All right, so homework, like I said, is given to you guys. It is a pretty lengthy homework assignment. The good news is pretty much everything that you guys are going to cover today we talked about before in section 3.2. So it's a pretty quick lesson. I actually skip over a couple of theorems that we've already talked about. So it takes us a lot less time to finish this lesson. So this is section 3.3. And it's based on increasing and decreasing functions. And we will talk about the first derivative test. We're not going to write it out because it's not anything that's new. You guys already know it. We just did it earlier. So we're going to talk about how to identify relative maxima and minima, or extrema in general, absolute maxima, absolute minima. And in order to do that, we're going to have to figure out how we can find if a function is increasing or decreasing. Okay, so there's a definition. I'm going to write it out for you guys. Again, something we've already talked about, but let's at least give this to you guys. So this is the definition of increasing or decreasing functions. All right, so there's two parts. It says a function f is increasing on an interval if for any x sub 1 and x sub 2 we have that x sub 1 less than x sub 2 implies f of x sub 1 is less than f of x sub 2. In other words, for every point that you move over to the right, okay, as the numbers for x get bigger and bigger, so do their height values. Okay, so the height of the first point is lower than the height of the next point, which is lower than the height of the next point, which is lower than the height of the next point. So that's how you can tell if something is increasing, when the y values are getting bigger and bigger and bigger as you move to bigger x coordinate. Okay, so if your x coordinate is increasing, so should your y coordinate. Okay, that's how you know that a function is increasing. Now, the second part is pretty much the same thing. It says a function f is decreasing on an interval if for any x sub 1 and x sub 2 we have that x sub 1 is greater than x sub 2 implies, it shouldn't be greater than, sorry, less than x sub 2 implies that f of x sub 1 is greater than f of x sub 2. So anyway, that's the definition of increasing or decreasing functions. Okay, so we've talked about this before. Like we said, if you notice that the function is increasing or decreasing, you can use a sign graph, right? Using that f prime of x, and then we do a number line and we check the pluses and minuses and all that stuff. That's another way that you can check. But this is just the main definition. Okay, so there's one new thing that we want to discuss. Now, we did see that when we were doing the sign graphs from before, that we would get pluses and minuses, right? And then you see like it would go from plus to minus or minus to plus, that type of stuff. So just a real quick FYI here. A zero derivative occurs at the critical points. It is a constant function and I'll just put in parentheses horizontal. Okay, so a zero derivative occurs at critical points. It is a constant function or horizontal. If I ever were to ask you, what is the value of the derivative at the critical point? What should your answer be? It should be what? 0. Right? If I ask you, what's the value of the derivative at a critical point? It should be 0. Okay? It could also be undefined. Why undefined? Well, let me give you an example. Think of the absolute value function. Right? The absolute value function has an absolute minimum at its vertex. Right? At the v, at the very bottom of the v. But what's the value of the derivative at the sharp edge? It's undefined, right? So the value of a derivative at a critical point is either 0, most of the time it is, or it could be undefined because it's a cusp. Okay? Remember that, please. Like I told you guys, there's some questions that are going to be coming up. They're going to be about stuff like this. Now, we also know a positive derivative results in an increasing function and a negative derivative results in a decreasing function. Again, this is all stuff that we've learned. I'm just rewriting it just to have it in terms of like documentation for it. But also, we've practiced it a couple times already. So this shouldn't be anything surprising. Okay? There is a theorem I'm supposed to go over with you guys, the test for increasing or decreasing functions. We already know how to test for that. Okay, so let's just go straight into the first example. So example number 1. So we're going to find the open intervals. Find the open intervals. And I'm going to highlight this because it's really important. We'll talk about why right now. But find the open intervals where f of x is increasing or decreasing. And f of x is given by x squared minus half x plus 2. Now the reason why we say open intervals is because a function cannot be increasing on a closed on the endpoints of a closed interval. Okay? For example, I'm going to erase this, okay? But if I were to have like a graph that looked like this, most people would say that right here, the graph at that point is increasing because they look at the stuff on the right side and they say, oh, it's going up, so therefore at the point it's increasing. But remember, I think I showed you guys once, I don't know if this graph has changed directions at that point. Maybe it's going back down, right? Or maybe it's continuing to go up. I don't know what's happening after that point. So I can't tell you what's happening at that point. I don't know if its derivative is 0. Maybe it's plateaued, right? Maybe that's the derivative at that point. It's flat. Maybe it's going up. Maybe it's going down. I don't know. Okay? So we can never say that a function is increasing or decreasing on a closed interval. We could say it's increasing or decreasing within certain parts. Okay? But you can never include the endpoints, okay? Never ever include the endpoints for a function when you're trying to figure out the increasing or decreasing interval, okay? So always should have open intervals when you discuss whether a function is increasing or decreasing, all right? So let's take our derivative here. That's what we're supposed to do. That gives us a 2x minus half, okay? Now to check to see if something is increasing or decreasing, we are actually going to set the derivative equal to 0. Okay, or you set it you set the denominator equal to 0 to see if you can make it undefined, but this has no denominators that we can actually set equal to 0, so I'm not even worried about that. Just set the function equal to 0. Okay, so we get that 2x equals to half, or that x is a quarter. Okay, once I find this critical number, I create my sine graph. And here's my 1/4. And what I'm going to do is I'm going to kind of use a little bit of scratch paper, right? So I'll just do stuff on the right side. I'm going to figure out what happens before and after 1/4. So I'm going to try a 0 and a 1, okay? So f prime of 0 and f prime of 1. That's what I'm going to work on, okay? F prime of 0 and f prime of 1. So f prime of 0, if I plug in a 0, I get 2 times 0 minus half. That's equal to negative half, which is basically negative. That's all I care about, right? The fact that it's negative. That's all I want to know. Okay? Now, f prime of 1, that's 2 times 1 minus half. Well, that's a 1.5. All I really care about is the fact that it's positive. So this graph is going down and then up. Okay, so they want to know where is it increasing, where is it decreasing. I'm going to say f of x. Notice not f prime of x, f of x. Because the purple line where I show it going down and then up, that's what the original function looks like. Okay, so f of x is decreasing from negative infinity to 1/4. Okay, and then I'm going to say f of x is increasing from 1/4 to positive infinity. What's happening at 1/4? Huh? Well, it looks like a cusp right there, but it's not actually a cusp. This is actually it's a quadratic function, right? Yeah, it's quadratic. So it's not sharp. My picture, the little skeleton I draw, there is a cusp there, but the reason why there's a cusp is because I haven't given it any curvature yet. And that's the second derivative test, which is concavity, but we're not there yet, okay? But think about the graph, an x squared graph. If that's a minimum, at 1/4, what kind of slope is it? It's 0, right? It's a horizontal line. Because what I just found out, that little skeleton graph is telling me that all the slopes before 1/4 are negative. All the slopes after 1/4 are positive. So that at 1/4, all my slopes are 0. Or not all of them. The slope at 1/4 is 0. Okay? So, there's my answer to this question, okay? To this problem right here. Now, at this point, I'm supposed to discuss the first derivative test with you guys, okay? But I'm going to tell you that we've already done it. Okay, I'm going to read it to you, and then you'll probably recognize it. It starts off with a whole bunch of really weird sounding information, but here we go. It says, let C be a critical number of a function f that is continuous on an open interval I containing C. What that means is, let's assume that you had a function, you took a derivative and you set it equal to 0 and you solve for x. Okay, your critical number. So in other words, find a critical number. So the way you find it is you take a derivative and you solve for x. Set it equal to 0, solve for x. Okay? That's what that first sentence said. The next sentence says, if f is differentiable on an interval, except possibly at c, okay, then f of c can be classified as follows. What that sentence means is, if you can take a derivative of that function everywhere, except for maybe the critical number. What are they talking about? Well, if you have an absolute value function, you can take a derivative everywhere on that curve except for there, at the cusp, right? But that cusp is a critical number, okay? It just can't be, it doesn't have a derivative, right? But you can tell the graph goes down then up, right? So that means that that would have been a critical number. It's just not differentiable at that point. So when they say, if f is differentiable on the interval, except possibly at c, that's what they're saying. They're saying maybe your critical number, you can't take a derivative there, but it's okay, it's still a critical number. All right? So far, in these two sentences, all they've said is, get your function, take a derivative, set it equal to 0, and solve for x. Okay, that's what they've said. Then they say, here are two things. If the derivative changes from a negative to a positive, what kind of extrema is it? From a negative to a positive. That would be a minimum, right? You can see one right here in the example above. From negative to positive, that's a minimum. And they say step 2, if it goes from positive to negative, then we call it a maximum. It could be relative, it could be absolute, we'll find out. Okay? But, and we've done this before, but that's what the theorem is basically saying. Look, take your derivative, set it equal to 0, solve, do a sign graph, and if it goes minus plus, then it's a minimum. If it goes plus minus, then it's a maximum. Okay, so there's a lot of writing that they want you to do. We're not going to worry about it. Okay, because we've already talked about it. So, and it's not one of those things you guys have to memorize, so don't worry about it. So, two more examples. Find the extrema of f of x equal to cosine of x plus 2 on the interval (0 to 4 pi). Now I want to take particular notice of the interval. Now normally when you guys do extrema, if your interval is closed off, then you're supposed to check your endpoints, right? But my extrema is excluding 0 and 4 pi, so that means I don't have to check my endpoints. Okay? Normally you check them if this side was like that and this side was like that. Then you would check 0 and 4 pi to see if those are extrema. But they're not. They're open. So since they're open, we can ignore them, okay? So pay close attention to that, all right? So let's do what we normally do. If we're going to find extrema, we got to take our derivative. So f prime of x, that's negative sine of x. The derivative of 2 is 0. And then I'm going to set it equal to 0. So negative sine of x equals 0, which means that sine of x equals 0. So what are my x values here? Now most of the time people would say, well, from 0 to 4 pi it would be 0, pi, 2 pi, 3 pi, and 4 pi. But remember, they're not including 0 and 4 pi. So I have 3 critical numbers total. Okay, how did I get those values? Remember, sine of x equal to 0. Well, sine is 0 when the angle is 0. The corresponding angle that kind of fits with 0, okay, would be pi, and then 2 pi, and then 3 pi, and 4 pi, 5 pi, 6 pi, 7 pi, right? Those are all 0 values. So I can't use 0 and 4 pi. Not that they're not answers, but they told me not to use them, right? 0 to 4 pi is excluded on the endpoints, so I'm not going to be able to use them. So I'm going to try my pi, 2 pi, and 3 pi. So I took my derivative. I found my critical numbers. Next step, actually not like that, is to do my sine graph. Now notice those are not arrows, those are open-ended. Okay, 0, 4 pi, open-ended markings. Inside I'll put a pi, a 2 pi, and a 3 pi. And what I'm going to do is I'm going to figure out whether this is increasing or decreasing, okay, based on my sine graph. So let's pick an angle between 0 and pi. So an easy one would be 90 degrees, pi over 2. Okay, because 0 to pi is 180 degrees, right? From 0 to 180. So we'll try pi over 2. So f prime of pi over 2. So that's going to be negative sine of pi over 2. Well, sine of pi over 2 is 1. So this is negative 1. So that makes this a negative. Now I'm going to pick an angle between pi and 2 pi's, from 180 to 360. So I'll pick 270, 3 pi over 2. Okay, so f prime of 3 pi over 2. That's negative sine of 3 pi over 2. Now, sine of 3 pi over 2 is negative 1. So that's negative of a negative 1. That's equal to 1. So that's a plus. Now, if I were to try an angle between 2 pi and 3 pi, I would try 5 pi over 2. Okay? It's going to come out to a negative because it's basically going to repeat what was happening in the same two quadrants earlier. From 0 to pi is the same as 2 pi to 3 pi. So that's going to be minus. And then 3 pi to 4 pi is the same as pi to 2 pi, so it's going to be plus. Because it just repeats itself, right? It's going up and down, it's oscillating. All right, so, go ahead. Huh? Oh, you were just stretching, sorry. So are you guys okay with how I explained 2 pi to 3 pi and 3 pi to 4 pi? All right, so it's just repeating, all right? So let's write out our findings here. And before I do that, actually, it's going down, then up, then down, then up. Okay? So let's write my answers here. F of x has a relative maximum. How many relative maximums do I have? No. Only one? Yeah, I would agree with that. Only one. Okay, you might see 2 more at the end, but remember those endpoints, they don't matter. Right? So there's just the one up there. So it has a relative maximum of something. Oh, I forgot to put that word, sorry. Of something at x equals something. We already know the x value, right? It's going to be 2 pi. But what's the height of it? So that means I got to go back to my original function. So let's see. F of 2 pi, that's cosine of 2 pi plus 2. Cosine of 2 pi is the same as cosine of 0, which is a 1. So 1 plus 2 is 3. So there's my 3. Okay, so it's a maximum of 3 at x equal to 2 pi. I'll change that 2 pi to purple, that way you can see that was done after. Relative minimums, how many? That's 2, right? So has relative minimums of something at x equal to something. You'll notice I didn't say, like, I didn't write has a relative minimum of this at x equal to this and has a relative minimum. So I didn't do it twice. I included both of them at the same time because since this is an oscillating function, it's going to reach the same minimum value every time. So since there's two of them, that means they're going to have the same value, right? So let's just find our f of pi. Cosine of pi plus 2. Now cosine of pi is -1 plus 2, so that's a 1. So that's going to happen at pi and at 3 pi. Okay, so I have relative minimums of 1 at 2 different places, relative maximum of 3 at 1 place. So before I stop with this example, think about the graph. Go ahead. Yeah. For this one it will, because it's oscillating. So it only goes a certain height up and a certain height down. So it's never going to go any higher than 3 and it's never going to go any lower than 1. So since the highest point of 3 only occurs one time, then I just list it as 1 point. But since the minimum actually occurs twice, then I can list them both under the same height. So that's why I did it. If they had different heights, then I would have listed it as 2 different relative minimums. But yeah, these are the same. So check this out. I call these relative minimums, but right now I just mentioned that they're not going to go any higher or any lower. So can I actually change their classification of relative to absolute? Would that be okay? Yeah, right? They're not going to go any higher than 3, and they're not going to go any lower than 1. So what I'm going to do is I'm just going to call it absolute. Because it's not going to go any higher than that value of 3. And it's not going to go any lower than the value of 1. Okay? So always go back and think about your answers and ask yourself, is that as high and as low as they're going to get? Because if it is, then I better change that to an absolute. Now, there's nothing wrong with calling it a relative maximum or a relative minimum, but it's more correct to call them an absolute maximum and an absolute minimum. Okay, so it's like those multiple choice tests when they're like, which one of these answers is the most correct one to pick? Well, calling them absolute would be more correct than calling them relative. Okay? Any questions on this one? Or any other questions on it? I guess we already had some. Alright, so last example, and we're done. I'm going to let you guys try this for a little while, okay? Alright, so let me give you a little bit of time, maybe about a minute or two to take the derivative, try to find your critical numbers, then I'll get started, okay? Alright, so now that you guys have had a little bit of time, hopefully this is what occurred. So you take your first derivative here. You got to get your power rule down first, so 2/3 times x squared minus 2 to the negative 1/3. And then the derivative of the inside is a 2x. So if I rewrite this thing, this will be a 4x over 3 times x squared minus 2 to the 1/3. Okay, give me a second here. Alright, so we're going to calculate some of the values. Let me get this out of this mode here. So Now that I have my derivative done, I'm going to set the numerator equal to 0. That's how I find my zeros, okay? Set the numerator equal to 0, which is just x equals 0, okay? And then I'm also going to get my denominator and set it equal to 0 so I can find what makes it undefined. So the denominator is this, and I'm going to set it equal to 0. So if I divide by 3, I get x squared minus 2 to the 1/3 is 0. I'm going to take everything up to the third power. So to get rid of that 1/3 power, so raise everything to the third power, I get x squared minus 2 equals 0. Add 2 to both sides, I get x squared equals 2. Take a square root, and I get plus or minus radical 2. So I actually have 3 critical numbers. 0, and then my plus or minus radical 2. So I'm going to make my sign graph here. F prime of x equals to, I'm sorry, not equals to. Sign graph looks like this. I'm going to put a 0 in the middle, a negative radical 2 here, a radical 2 there. And what I'm going to do is I'm going to graph that function, okay? The derivative function, because I want to plug numbers into the derivative function. So I'm going to graph the derivative function. Let me put 4x divided by 3 times x squared minus 2 to the 1/3 power, and put one more parenthesis here to close that off. So there's my function, and this is what the graph of the derivative looks like. This is not the original function, okay? This is the graph of the derivative. Now the reason why I graph the derivative is because I want to figure out the values for numbers less than negative radical 2, between negative rad 2 and 0, 1 to rad 2, etc. So I'm going to create a table. So I'm going to go to table set. I'm going to hit second and then table set for myself. And under independent, I want to go to ask. Okay, I want it to ask me what numbers to plug in. So now that I've done that, I'm going to go to my table. So second table, and there it is. That's what it looks like. Now this is going to give me the values of the derivative because that's the one I'm graphing, right? So I'm going to plug in a negative 2, which is less than negative radical 2. So let's try negative 2, and the answer is negative. So I'm going to put minus. Okay. And then I'm going to plug in a negative 1, and the answer is positive. Then I'm going to plug in a positive 1, and my answer is negative. And then I'm going to plug in a positive 2, and the answer is positive. So that means that the original function looks like this. Down, up, down, up. Okay? Now if we look at the graph that I have, you might say that is going up, down, and then up eventually. Right? It's going up and then down again and down and then up, right? You're like, that's not what we got. Well, yeah, because when you do the sign graph for the derivative, the skeleton that I draw is showing you what the function looks like, not what the derivative looks like. Okay? Now, let's graph the original function just to see it. The original function, let me turn off this graph here. Turn that off. The original function is, I forgot, what was it? X squared minus 2 to the 2/3. Let's look at the original graph. Is that graph going down, then up, then down, then up again? Yeah. Now, it doesn't look like my graph perfectly, but it does kind of do the motions of my skeleton graph, right? So anyway, let's get back to this. All I have to do is tell it relative maxes and mins. Look at the original graph. Are those absolute minimums? Yeah. Is that an absolute maximum? No, it's a relative maximum, but two absolute minimums. So let's write that down. F of x has absolute minimums of something at x equal to plus or minus radical 2. If I want to figure out what those somethings are, let me just go to a table and plug in a negative radical 2. And yikes, that's the wrong thing. Radical 2. So 0. That's the absolute minimums of 0 at x equal to plus or minus radical 2. And then f of x has a relative maximum of something at x equal to 0. Let's figure out what happens at 0. 1.587, so I'm going to put 1.587. So there's the end of the lesson. You guys have your homework already?